welcome you all in the 19th lecture of Electronics Measurement and Instrumentation. This is part 2 of Wattmeter. In last lecture I have discussed about what are the different application of Wattmeter, what we are measuring with the Wattmeter, and I have also discussed about the electrodynamometer type of Wattmeter. In this lecture I will discuss the induction type Wattmeter and the Wattmeter that is used for the 3-phase supply. So, this is the outline of my lecture. I will discuss first the construction of induction type Wattmeter, then derivation for deflecting torque, advantage disadvantage of induction type Wattmeter, and then the power measurement in 3-phase supply circuit. So, induction type Wattmeter induction type instrument consists of one series magnet and one shunt magnet. So, shunt magnet is known as shunt magnet because it is connected in parallel to the load. So, the current which is flowing in the shunt magnet is proportional to the voltage of the load, and the series magnet is connected in series with the load. There is an aluminum disc, and this aluminum disc is rotating because of the eddy current, because of the flux between these two magnets, and there is a braking magnet that is used for the damping purpose. So, induction type meter has two fluxes are produced by two different alternating currents on a metallic disc. Due to alternating flux, there is an induced EMF. The EMF produced at one point interacts with the alternating current of the one side resulting in the production of torque. Hence, due to these two torques which are in different direction, the metallic disc, that is the aluminum disc, it is made up of high resistive material and this will move. So, now induction wattmeter, construction of induction wattmeter. Induction wattmeter consists of two laminated electromagnets. Lamination is required because it reduces the eddy current loss. So, it consists of two laminated electromagnet, one electromagnet called shunt magnet. So, this is electromagnet, this is the shunt magnet. This is known as shunt magnet because we can see that it is this terminal is in the coil is moving like this way, and it is connected in shunt with the load. The second is a series magnet. A shunt magnet is made up of very high inductive, so that the current and the flux produced by the current, they will have a 90 degree phase difference. So, the current in this magnet is made highly inductive, so that the current and the produced flux, so produced flux and current lag behind the supply by 90 degree. The other coil is series magnet, known as series magnet, and it is connected in series with the supply and it carries load current. The coil of this magnet is made highly non-inductive, so that the angle of lag and lead is wholly determined by the load. Now, a thin aluminum disc is mounted on the spindle. We can see here this is the shunt magnet and this is the series magnet, and so an aluminum disc is placed in between these two magnets, and this aluminum disc is made up of high resistive material, and that controlling torque, this is the moving part, and this aluminum disc needle is also attached with this aluminum disc. So, this needle will move. So, to control the movement of this needle or the aluminum disc, a spring is provided. So, here the controlling torque is provided by the spiral spring, and in this induction type of wattmeter, the damping is provided by the electromagnet. Means here the damping is not the air friction damping, but it is through the electromagnetic damping is provided, and it is through the permanent magnet. So, we can see that one permanent magnet is here and the disc is placed in between that permanent magnet. So, this permanent magnet produces eddy current, and because of that the controlling this damping torque is produced. Then there is 2 or 3 copper rings are also in the mid of this. If we see this diagram, so in the middle of this 2 coil, fixed coil, there is a copper ring, there is a central limb, and on the central limb 2 or more copper rings are provided. This is also called shading rings, and it provides by adjusting this position of these rings, the shunt magnet flux can be made lag behind the supply voltage exactly 90 degree. So, we in this wattmeter in this wattmeter it is a requirement that the shunt magnet flux lag 90 degree behind the supply voltage, then it will accurately measure the wattage of the instrument where it is connected. So, now the deflecting torque equation for the induction type. So, as we can see, V is the voltage to be measured, I is the current to be measured, phi is phase angle between current and voltage, phi sh is flux by the shunt magnet, flux produced by the shunt magnet, phi se is flux produced by the series magnet, and ESH is EMF induced in the disc by the flux of the shunt magnet. ISH is eddy current flowing in the disc caused by the shunt magnet. Similarly, ESE is the EMF induced in the disc by the flux of series magnet. ISE is eddy current flowing in the disc caused by the EMF. So, we can see in the vector diagram this V, the voltage and current, there is an angle between voltage and current, that is phi. This flux produced in the shunt coil, flux produced due to shunt coil is having a 90 degree with the voltage, and this is also having a 90 degree with the EMF induced by this. So, here is 90 degree and this is also 90 degree. So, to produce that this flux is having a 90 degree with the induced EMF, we need that the shunt coil should be highly inductive. So, making shunt coil highly inductive and by adjusting the copper ring, this is maintained ESE and Q phi SE 90 degree phase difference between this, and V and phi SH the phase difference 90 degree between these two. Next, we are keeping the aluminum disc highly resistive, so that the current ISE is in phase with the ESE, and similarly the current ISH is in phase with the ESH. Now, this is the vector diagram. So, by this vector diagram we will solve, we will see whether the deflecting torque is proportional to the power or not. So, now first the interaction of current ISE with coil with flux phi SH produce torque T1. Suppose the current of the series coil with the flux produced by the shunt coil, this produce a torque which move the disc, aluminum disc. So, it is T1 is equal to K SE phi SH cos phi. Here the angle between ISE and phi SH is phi degree. This is the 90 degree, so it is phi degree. Then interaction of current ISH, the current in shunt coil with the flux of produced due to the series coil produces a torque T2. So, T2 will be K ISH phi SE cos 180 minus phi. If we see the phase angle between ISH and, so this is ISH and this is phi SE. So, here the difference is 180 degree minus phi. So, it is 180 degree minus phi. Now, we know that the torque produced by both the shunt coil and the series magnet, both coils have opposite torque. So, torque total deflection torque T d is equal to T 1 minus T 2. So, we will substitute the value of T 1 and T 2. So, it is K ISE phi SH cos phi minus k sh phi sh cos 180 minus phi. So, it is cos 180 degree minus phi is equal to minus cos phi. So, it is minus minus plus. So, it is k 1 and this ISE into phi sh and ISH means current in shunt coil into flux produced by the series coil and current in series coil and the flux produced by the shunt coil. These are they both are the proportional to the voltage and current that is flowing in series and shunt coil. So, it is now this we can replace it by VI K1 VI. So, it is K1 VI cos phi and K2 VI cos phi. So, total deflection is equal to K VI cos phi and these constant K1 and K2. So, here we can see that the deflection torque is equivalent to the this term and deflection torque is proportional to the power measured in the circuit. So, by this we can see that we can measure the power by using this induction meter. So, what is the advantage and disadvantage of induction motor? The induction wattmeter. So, induction wattmeter produces an uniform scale, it is very robust in construction, it is unaffected by the stray magnetic field. As we have seen that electrodynamometer type instrument are affected by the stray magnetic field, but this instrument is not affected by the stray magnetic field because the deflection torque of this instrument is very high. And disadvantage is the biggest disadvantage that we can't use this instrument for the DC measurement, it is only used for the AC measurement and it consumes little bit more power than other instruments and its accuracy is low because the moving part, that aluminum disc is heavy and it also affected by the temperature variation. So, difference between dynamometer type and induction type wattmeter is that dynamometer type wattmeter we can use for AC and DC both, in induction type instrument only we can use for DC measurement. This dynamometer type instrument has high degree of accuracy because it is if it is carefully designed, and this induction type wattmeter has low accuracy. Similarly, dynamometer type wattmeter power consumption is comparatively low, induction type meter has high power consumption. Then the weight of the moving part in dynamometer type is comparatively low, whereas the weight of the moving part is comparatively high in the induction type. So, these are the basic difference, and the second the last difference is that dynamometer has a comparatively weaker working torque, whereas the instrument induction type instrument has comparatively more effective working torque. Now, the power measurement in 3 phase. So, there is a Blondel theorem, that this theorem states that the power provided to a system of n conductors is equal to the algebraic sum of the power measured by n wattmeter. The n wattmeter are separately connected such that each one measures the current level of one of the n conductor and the potential level between the conductors and a common point. In the further simplification, if that common point is located on one of the conductors, that conductor's meter can be removed and only n minus 1 meters are required. So, we can measure 3 phase we want to measure the power of 3 phase circuit. So, we can measure it by using 3 wattmeter method, or as per the theorem of Blondel, we can use 2 wattmeter method by making one common terminal, and we can also measure this by a single wattmeter by switching between two terminals. So, first we will study the measurement of 3 phase power by 3 wattmeter method. So, if we are having a star connection, so in a star connection there is a common point. So, as we see in the diagram that we know that in wattmeter there are 2 coils, one is power coil and other is the current coil. So, voltage and current coils, there are 2 coils. voltage coil is connected between the voltage coil is connected across the load and current coil is connected in series with the load, so that it can read the value of current. So, here we can see this is the current coil and current coil is connected in series with this meter. So, this is the common point. So, this is the common point. So, all the wattmeters voltage coil is connected to, power coil is connected to this common meter, common point. So, common point is connected. So, the first wattmeters power coil is connected to this point, second wattmeter power is connected to this point, and the third wattmeters coil is also connected to this point. The current coil is connected in series. So, current coils are connected in series. Each wattmeter will give the reading as product of phase current and line voltage. So, the resultant sum of this is P1 plus P2 plus P3, and so each wattmeter will give V1 I1, the first one will give V1 I1, second one will give V2 I2 and third one will give V3 I3. So, it will produce the total power of when we take the sum of all the wattmeters, then we will get the total power of this circuit. So, this is the 3 wattmeter method. Now, if we have 2 wattmeter method, so if we have 2 type of connection here, one is star connection of the load and second is delta connection of the load. So, first I will discuss the star connected load. So, in star connected load, the reading of wattmeter, one is the product of phase current and voltage difference. Similarly, the reading of wattmeter 2 is the product of phase current and the voltage difference. So, here we can see that the first wattmeter has a current I1. So, it is the product of I1 and the voltage difference is, if we see, the V1 minus V3. So, first one is having a current I1 and voltage difference V1 minus V3. The second wattmeter is having current I2 and the voltage difference we can see V2 minus V3. So, second is having V2 minus V3. So, when we simplify it, we will get I1 V1 this product, then minus V3, V3 is taking common, then it is I1 plus I2 and then this term I2 V3. Okay. So, no, sorry, I2 V2. Okay. So, but we know that the sum of all current is 0. So, I1 plus I2 plus I3 is 0. So, hence we know that I1 plus I2 is equal to minus I3. Okay. So, when we will put I1 plus I2 in place of minus I1 plus I2 is equal to minus I3, then we will get total power, that is I1 V1, and in place of I1 plus I2 we will put minus I3. So, it is minus minus plus. So, it is I3 V3 and here I2 V2 is there. So, we will get total power by using 2 wattmeters. Now, in delta connection, again we will use 2 wattmeter and will connect the power coil common between third terminal. In first terminal we have connected 1 wattmeter, in second we have connected 1 wattmeter and the power coil of both the wattmeter is connected to the third terminal. So, the first wattmeter has a reading of P1 is equal to the current that is flowing here is this I1 direction of the current of I1 direction is this one and the direction of I3 is this one. So, it is I1 minus I3 and the voltage V3 is of this direction. So, it is minus V3. So, the first wattmeter P1 will produce minus V3 I1 minus I3. Similarly, the wattmeter 2 will produce V2. If we see wattmeter 2, so it will produce V2, this is the voltage, and if we see the current, then the current is I2 in this direction and I1 is in this direction. So, it is I2 minus I1. So, P2 is equal to V2 I2 minus I1. So, total power P is equal to P1 plus P2. Now, when we add this, it will be V2 I2 plus V3 I3 minus we take common I1 V2 plus V 3. Now, we know in delta connection sum of all the voltages will be 0. So, it is V 1 plus V 2 plus V 3 is equal to 0. Now, we can substitute in place of there we have V 1 V 2 I 2 term, we have V 3 I 3 term. So, we can replace in place of V 2 plus V 3, we can write V 2 plus V 3 is equal to minus V 1. So, here we can write V 2 plus V 3 is equal to minus V 1. So, total power P is equal to V 1 I 1 plus V 2 I 2 plus V 3 I 3. So, in this way we can measure the voltage the power of the 3 phase circuit, which is in the where the load is connected in delta method. Now, 3 power phase power by 1 wattmeter method. So, by 1 wattmeter method we can connect the wattmeter at one place and we can apply switch. So, there is switch, when this switch is when we close the switch 1 and 3, then it will connect this wattmeter in between 1 and 3 terminal. So, the current coil is again connected in series, but the pressure coil is connected in the parallel to this. So, pressure coil is here, and when the switch is at position this 3, when we connect the 1 to 3, then what will happen? It will measure the power between first and third terminal. So, this method and this method, when we want to measure 3 phase power by 1 wattmeter method, the load should be it should not be unbalanced load, the load should be balanced. If it is unbalanced, then proper measurement is not done, proper value we will not able to achieve it. So, therefore, here in the balanced load I 1 is equal to I 2 is equal to I 3, all currents are same, and V 1 is equal to V 2 is equal to V 3 is equal to V. So, first by closing the switch 1 3, we get reading of the wattmeter 1, and since it is 3 phase connection, so it the power of first wattmeter when it is at position between 1 and 3, P 1 is equal to V 1 3, the voltage difference between one terminal and 3, and then the current which is flowing through this, and multiplied by cos 30 minus phi. So, V 1 3 is equivalent to root 3 V I, okay, root 3 V. So, it is root 3 V I cos 30 minus phi. Similarly, we can get when we switch we place this switch at position 2, then we will get the reading between 1 and 2. So, this P 2 is equal to V 1 2 I 1 cos 30 plus phi, and again this V 1 2 is equal to root 3 V. So, it is root 3 V I cos 30 plus phi. So, when we add both the power, we will get 3 V I cos phi. So, in this way we can measure the 3 phase power of 3 phase circuit by using 1 wattmeter method also. So, now in this lecture I have covered the measurement of power by induction type wattmeter, and I have also covered the measurement of 3 phase power by using 1 wattmeter, 2 wattmeter and 3 wattmeter methods. So, that is all from my side. Thank you all.